I was standing on a bluff the other day watching this massive ship drop anchor, and it just got me thinking about that simple curve of the chain trailing into the water.
Hmm.
Or, even simpler, the power lines between two telephone poles. We see that sag every day, and I think most of us just assume, oh, that's a parabola.
Right. It seems like it should be.
But here's the riddle for this deep dive. Is that curve really a parabola?
And the answer, if that chain is just hanging there freely under its own weight, is almost certainly no.
Okay.
Today, we are diving into the catenary. It's the mathematical curve of that idealized hanging chain, and it's totally distinct from the parabola. It's actually the graph of the hyperbolic cosine function.
Hyperbolic cosine. That sounds intense.
It's actually really elegant. Think of it this way. It relates to a hyperbola in the same way that your standard sine and cosine functions relate to a circle.
Okay, let's unpack this then. The history, the physics of why this shape matters so much, and where it pops up in unexpected places. That's our mission for this deep dive.
And what's so fascinating is that this question, it stumped some of the greatest minds for decades. I mean, Galileo, back in 1638, he knew it wasn't a parabola.
He knew it wasn't.
Yeah, he sensed it, though he did say it was a pretty good approximation when the curve isn't sagging too much. But the actual equation wasn't figured out until the late 17th century.
Which makes what Robert Hooke did in 1675 even more incredible. He published this famous anagram.
Right, which, when he finally decoded it, provided this key architectural insight.
As hangs a flexible cable, so, inverted, stand the touching pieces of an arch.
And that single idea is the core principle of structural efficiency. You take a catenary, you flip it upside down, and all those tension forces in the chain, they become pure compressive forces in the arch.
So all the forces are just pushing straight down through the material.
Exactly. It completely eliminates what engineers call internal bending moments.
And what are those? What's a bending moment?
Think of it as any force that wants to twist or snap a beam. By getting rid of them, the arch only feels this pure squish, which maximizes its stability. It's why Gaudí used them all over the place, like in Casa Milà. It's form-following physics.
So if we look at probably the world's most famous arch, the St. Louis Gateway Arch, is that the perfect example?
Ah, that's a great question. It's the perfect example of a weighted catenary.
A weighted one.
Yeah, if you look closely, the base of the arch is much, much thicker than the top. So the weight isn't uniform. The curve is mathematically adjusted to handle that extra compressive load near the ground. It's a brilliant bit of optimization.
So if architecture loves the catenary, where does the parabola finally get its moment to shine? I'm thinking bridges.
That's the crucial distinction. A really simple suspension bridge, where the road itself just follows the cable's curve, that's a true catenary. The cable is just holding its own weight.
But the big ones, like the Golden Gate, they have a flat roadway.
Exactly. And when that flat roadway's weight is so much greater than the cable's weight, the load changes. It's not distributed along the curve anymore. It's distributed uniformly horizontally. And that uniform horizontal load is what creates a perfect parabola.
That makes so much sense. One is carrying itself, the other is carrying a flat street.
Precisely. And there's another bit of mathematical beauty here. The tension, T, at any point in the chain has this simple linear relationship with its height, y. T equals YY.
Meaning the higher you go on the chain, the greater the tension.
In a perfectly predictable way. It lets engineers calculate material needs with incredible precision.
That theme of precision and efficiency just keeps coming up. And speaking of insightful help and efficiency, this deep dive is brought to you by Embersilk. If you need help with AI training, automation, software development, or even just uncovering where AI agents could make the most impact for your business, check out embersilk.com for your AI needs.
Let's bring it back to that ship you saw at the beginning. That's one last, really surprising application. Marine anchoring.
Oh, right, the anchor chain.
A heavy anchor chain is designed to create that slack catenary curve. That shape ensures a lower angle of pull on the anchor itself,
right,
which dramatically increases its holding power. It's security through geometry.
It really is nature's optimal design. It's always looking for the shape of least potential energy.
Yeah.
And you mentioned if you spin that curve.
Yes. If you rotate the catenary, you get a shape called a catanoid. And a catanoid is what's known as a minimal surface. It's the shape a soap film makes between two rings.
Wow.
It's the smallest possible surface area for that boundary. And so for a final thought, consider this. That same foundational principle of minimal energy, of ultimate efficiency, is now being used to design things like micro-optical devices and optimal filaments in high-efficiency lamps.
So the same physics in a hanging chain is driving modern tech.
The ingenuity of nature discovered centuries ago is still pushing our progress forward today. It's beautiful.
Thanks for joining this deep dive into the mathematics and physics of the hanging chain. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.